Welcome to the last week of lectures on algorithmic sides of this course. In this week, we would like to talk about Matroids, but we will be talking about representative sets. Okay, it's a technique which was developed. It has been around for quite a while, but it was only developed in a proper way around 2012, and and it gave lots of interesting answer from 2012 to 2016, 4 or 5 years. It's also now quite useful technique to have. So we'll talk about that. So the problem we will be interested in is in directed k path, and that is where we will build our theory. Right. So we will be talking about directed k path. So as you all know, input is going to consist of a directed graph G, okay, a positive integer k, okay, parameter is definitely k. And the question we will try to address does there exist a k path or a path on k vertices, rather path on k vertices. Okay. So for this problem we have seen several algorithms. So let's just go back to what we have learned. Several algorithms we have seen. Okay. Okay. So the first algorithm we would have seen is via color coding. Okay. That algorithm ran in time 2 e to the power k n to the power 1 randomized. But you could also design a deterministic algorithm for this using hash functions. Okay. So in fact, let us say 2 e to the power k n to the power bigger 1 deterministic. Okay. Deterministic. And then last week of our lecture, we saw an algorithm based on algebraic techniques, right? Algebraic techniques with running time, if you recall correctly, was 2 to the power k n to the power 1. Okay. And this algorithm was randomized. Okay. Okay. So furthermore, this is important to point out that for directed k path, k path, okay, 2 power k n to the power bigger of 1 algorithm is the state of art. Okay. So the open problem in the area is, one of the good open problem is the good open problem in the area is, first, design 2 minus epsilon to the power k n to the power big O of 1 time algorithm for directed k path. Okay. In fact, what is not also known is to design 2 minus epsilon to the power n number of vertices time algorithm for directed Hamiltonian cycle. So this will be like directed k path or directed. So given that these are big open problem in the area, I just wanted to mention, but today we will not be talking about an algorithm which is anytime better than 2 power k algorithm, but rather a different algorithm. We are going to talk about a bit more natural algorithm, let us say, okay, a bit more, in my view, a natural way of designing algorithm. Okay. The running time of our algorithm will be k to the power big O of k actually, but we will point out how this can be at least made to work in time, at least say 4 to the power k plus little of k n to the power big O of 1. I will point this out to you. Okay. But besides those, okay, besides those, we will see several other applications. Okay. So, let us straight away jump to the technique, jump to the technique. So, let us try to understand. So, for that we are trying, suppose you are given a graph G and you are given a 2 vertex U and V, and you are looking for finding a path K. Okay. So, now I am going to define a family P, U, V and P. So, what is the P, U, V, P? This is basically, let us say, how to say this, what is the right way of saying this? Let me tell you 1 second. Okay. So, this is basically consisting of set X, okay, okay. Cardinality of X is equal to P, and there is a directed path, starting at, okay, I think let us say ST. So, what is this? I am going to starting at U, ending at V. Okay. So, think of what is going to consist of. So, now suppose I have a U, and or rather suppose I have S and T, and I do have a path of say length k between them. Let us take some W, right. Is it possible that there are paths, this is one path, directed path, this is another directed path, and this is another directed path, there is another directed path, right. So, I fix an integer p, okay, I fix an integer p, and I ask how many paths or how many prefixes of paths or how many subsets of these vertices are there who could potentially reach to T. So, these are like a partial paths, these are p length partial paths. So, like they are not, so, but if you notice here, rather than talking about path, I am talking about set, because it is possible that to reach from S, like look at the first p length, there could be a same subset, but there could be different paths because of the route. We do not care about what route internal they, but all I care about that if I start from S, okay, and I fix some vertex, how many ways can, like what are the subset of vertices which could take me S to W, right, by a path, okay. So, this is how PPUVX is defined. So, what are these? These are basically, if you notice, these are subsets of vertices, right, and of course, X is going to rather let us say u and w. Okay. So, subset of vertices x is going to have definitely u and w first of all, and so these are those vertices. So, those vertices, so you start from u, you end at w, and look at so other vertices like x minus u comma w. There is a path from u to w which uses all the vertices of x minus u w, right. So, and I wrote x, right, not as a permutation, because it is possible that the vertices of x minus u w, there could be several paths, and then the vertices of this set could be occurring in a different sequence. Okay. But we are not caring about that, we are only caring about sets. So, basically you can think of this, we could think of as p length prefixes or p length prefixes. So, that is the whole idea, but we do not have to say this. We could just say that these are nothing but, what is this? It is those vertex sets, of course, containing u and v that can be realized as a path of length p between u and v. Okay. Right. Okay. So, now let us look at P, S, T and K. What is this? This is going to be set of vertices containing S and T of size k that can be realized as a k length path between S and T. So, what is our question? So, our question can be reformulated. Our question can be reformulated as follows. Okay. So, what is our question? Our question is okay. So, if it is non-empty, then we know that there is a path from S to T. Okay. Fine. But naively, if you notice, okay, naively, what could be the size of this? Well, this could be as bad as choose k minus 2. Example, click. Right. So, if you take a clicks on n vertices, okay, and you fix two vertex S and T, then you look at any other k minus 2 size subset, you could. So, PKST could roughly be, let us say, n to the power k, or so in particular UV could be as bad as n to the power p. So, directly computing this set, okay, direct computation, directly working with P UV does not seem to give us anything better than XP algorithm, or rather this is like a brute force or naive or whatever you want to call it. Okay. Okay. But so then we ask ourselves question, could be or rather, before the phrase the question, so let's say, let's look at this. Okay, and here is W, here is B, and there are, and suppose this is the set P U V, and this is V, and there is a say path from U to V of length K, right? Okay, but like all you see is this. Okay, all you see is this, and this is some family which you don't see. Okay, this is some family F, or which is we know it. Okay, why do I need? Okay, and suppose this is there's a path of length. Okay, but which is like so this is fixed. So every path in PPUV starts at U and W and everything, and I know this. Okay, let's call this part of the path B, and suppose there is a path A. Okay. Okay. Now so what the property of this path is? The first property is that, notice that A, of course, which is UW is there, subset, intersection B is equal to phi. So for the path P that we have, which starts at U, goes via W, and suppose this is P. Okay, so the first part, let's call it A and let's call it P. Okay. Now let's ask ourselves, what happens if we give you another A prime such that all I can say you that I don't know whether what I do, such that all I can say to you that A prime intersection B is phi. Okay, all this is all that I can guarantee you. I don't know any relation between A and A prime, but we know that A prime intersection B is phi. So if I can give you, so I don't know how to, but suppose some magically I tell you that, look, I do have a set, some other set, I have a set A prime, but and I know that A prime intersection B is phi. So what do we have? So we have an A prime element of UV such that A prime intersection B such that A prime intersection B is empty. So at this point of time, pause this video for a minute and ask yourself, if I did have such an A prime, can I do something with it? So if you notice, so I have this path, okay, I have this path U, W, U, I think I have been, this should have been V, yeah, so sorry, this should have been V, my bad, this should have been Yeah, so this is fine, this is fine, this is fine, this is fine. Okay, and this should be this is W. Okay, this we can drop it. Okay, okay. Okay, so you gave me such a V. W. Now I know this is A, but you also I know that A prime is in PPUV. It implies that there is a path on A prime with U as starting point and V as the last vertex. Last vertex. Great. Let that path be P. Let that, okay. So all I know at this point of time that look at that path. Okay, so there is a path on set A prime. So there is a path with this. Okay. Okay, and notice because that path A prime intersection B is phi and this is B, right? Now let's call this brown path and blue path. So now if you concatenate brown plus blue path, okay. So brown path you go from U to V and blue path you go from V to W. This is still a path of length K. This is a path of length K. So to have a path of length K at any point of time, I don't need to this tells us that look, if I have a set, okay, if I have a set, so look what we had, we said look in PPUV I am trying to keep all partial paths of length P, okay, and I know that I would like to keep all those sets which could potentially be grown to or rather that way could be. So the question be phrase, okay, question, okay, question could be find a set or family, okay. So this is the setting which we are in. So now just to phrase this question nicely, let's make it slightly let's put it in an abstract setting, okay. So what is my abstract setting? So I have universe, okay, and I have family of some, say I have FP, okay, family of subsets of U of size P. This is what I have, okay, rather, okay, this is my F, and what I would like to keep, what want to get is F hat, which is a subset of F with the following property. For or rather I want to have this property that if okay, if there exists a set B for which, if there is a set B of say size Q, for which there exists a set A in our family such that A intersection B is empty, implies there exists a set A hat in F hat such that A hat intersection B is empty. Okay? And so we will not talk about, so right, so huge universe and Q is an integer. Okay. So let's try to understand what happens. So basically what happens is that here your universe, and suppose this is your family F. So what you want to achieve is a smaller subfamily here which preserves disjointness. In what sense? So this is like F hat. Okay. So what I mean by this, so suppose you give me a set B from some set B, then I say, I do have a set A such that A intersection B is phi. So for example, for every set B of size Q of universe, okay, if there exists a set A in your family which is disjoint from this, then you need to guarantee there exists an A hat in F hat such that A hat intersection B is phi. Okay. Okay. So that is the kind of property we would like from F hat, right? And so so the reason why I put it into this is because this is the same kind of situation which our path problem was motivating, because for the path U will be vertex set of G, Vg, and what is my F is like PPUV. So just to, okay, so abstract to this thing. So in path case, U would have been equal to Vg and PPUV would have been our family, right? That's it, right? And Q would have been K minus P. That's it. Okay. Okay. So that's it. Okay. And so okay. Okay. So definitely, clearly, for F hat we can take F. Okay. But we will show to you in a minute that there exists a much smaller F hat. Okay. There exists much smaller F hat, and okay. 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 So there exists much smaller F hat. So okay. Okay. So just to do that, let's say consider F hat subset of F which is minimal. What is the meaning of this? Let's try to understand. Okay. So what will be the meaning of minimal? So meaning of minimal should be, right, suppose A is an F hat, implies there exists B, okay, of size Q such that A intersection B is empty, and for all A prime in F hat minus A prime intersection B is not equal to it, right. So in other sense, I have this A because there is a set of size Q, okay, with which this set is disjoint, and every other set that I have kept in my family, okay, they are not disjoint, they are intersect with it, right. Because then I know that because for every set B, if some other set would have been disjoint with like disjoint, then this A is of no use, because for every set B for which okay, so so what is the meaning of this? Okay, so the meaning is that, look, I'm going to keep A in F hat, because if there exists a B of size q such that A intersection B equal to phi, then for every A prime in this set, okay, A prime intersection B is not equal to phi, meaning the set of objects that I have kept has the following property, is that for every set that I have kept, there is some set which it is disjoint with, but it intersects with every other set. So this is what I mean by minimal. Okay, so let's consider. So suppose, okay, so let F hat be a minimal subset of F, let's call, say, satisfying disjointness property. Let's call it disjointness property. Okay, minimal subset of this. So, okay, and let's say F hat is A1, A2, A let's say M. Okay, so there are M sets. Okay, now because they are disjoint, and okay, and always recall that each set has size p. Okay, but they are minimal. It means for A1 I will be able to find B1. Okay, for A2 I will be able to find B2. For AM I will be able to find BM, and what will the property? AI intersection BI is empty if and only if AI Bj is equal to empty, if and only if I is equal to j, right. So A1 and B1 do not intersect, but A1 intersects with everybody else. So if, let's draw an edge if they intersect. Okay, so then A1, right. Look at A2, there will not be an edge. Look at AM, right, except this, right. So this is how it is going to be. Now you ask ourselves, right, we took any minimal set, right. Any minimal set has a property that for each AI we could find a set Bi such that that Bi intersects with every other AI, every other Aj except the AI. So we have the property that we have these pairs of sets A1, B1, right, and what is size? What is the and what is the property of each of these Bi's? That each of the Bi's has size some set Q. Okay. So this is another. So this is like a what is called two families theorem. Okay, this is exactly precisely what is called two families theorem. Okay, what is two families theorem? Okay, so the two families theorem is, so we have universe, we have pairs AI Bi, I equal to, okay, AI Bi, I like some M, okay, I going from 1 to M, okay, and what is this? All cardinality of EI is B, all cardinality of BI is Q, okay. So notice that we were trying to do this and we say, look, they must satisfy this property. So now let's, okay, is equal to Q, and AI intersection Bj equal to phi. Okay, so let's say this is not cleanly written, so let's, okay, so this brings us to what is called classical two families theorem, okay, of Bolovus. Okay, it's also called two families theorem. Okay, so what are given to us? We have given to universe, and pairs of sets ai bi 1 to some m sets with the property that ai intersection bj equal to phi if and only if I equal to j. Of course, each ai has size p and bi has size q. Okay. So, this is what, okay. Then m is less than equal to some number. Okay. We will get that. Okay. Okay. So, in fact, what we will show that m is less than equal to p plus q, which is p. Okay. So, in fact, the number of such pairs that we could obtain is upper bounded by a function of p and q. It does not depends on the size of the universe. Okay. Then it would imply that f hat had size p plus q choose p. Okay. And so that's great, right? Because so now let's try to prove this. So now what we will do in the next lecture, that now that we have set up all these things, in the next lecture we will first prove the lemma, so a bound on f hat, and then we will consider a question about computation of f hat given f, and then usability for parameterized algorithm. Okay. So, that is what we will do in the next lecture.